So hello, this is Jude. This is my Unit 3 video on target and tissue reactions. So I'm going to talk first about the two different kinds of target interaction. Bremsstrahlung interaction and the photoelectric absorption interaction. So Bremsstrahlung is a German word. It means braking. Bremsstrahlung radiation happens when your incident electron or your photon being transmitted from your X-ray beam is going into the atom of a target, and the nucleus of the atom itself is keeping it from colliding. It's like a repulsion force that's being generated, and it's also causing it to slow down and break. So it's depending upon the energy, of course, that's being transmitted from one to the other. But in general radiography, this is the most common interaction that happens. And that other part is the photoelectric absorption interaction. And this is 15% of our tissue interaction, but we'll talk about that a little bit more. So your photoelectric absorption happens when your incident photon collides with an inner shell electron. And once that electron gets kicked out of its shell of sort, it becomes ionized, unstable. So there's an outer shell electron, or close in proximity electron, that fills in that vacancy really quick. And then, well, it keeps cascading and filling in, because the one that just filled in one now has an open spot too. So they all fill in of sorts, and that's like a cascade. And then every time that one happens, of course, it emits a photon. And all this happens until it returns to normal, non-ionization. But in order for photoelectric to happen, the energy of the beam itself must be higher than the binding shell energy. It's the force that's keeping it within the shell itself. Okay, so this is say this is a 30 keV beam, and this is a 31 keV shell. It's not going to do anything. It's too low. It's no, get out of here. But however, if it's 31 or more, then it's going to knock that one, and we're going to have some photons made then. Okay, so other different kind of tissue interaction is coherent scatter. And your coherent scatter is very, very low energy. Of course, there's two different kinds. Thomson, which involves just a single electron moving a little bit, and Rayleigh involves when all of them are kind of moving. Basically, it vibrates because of its low energy. I kind of see it as like cruising by, or maybe, Amy's truck driving by with the leaves. There's no energy that is being transferred, so this is not ionized. And the other 85% of tissue interactions that happen within diagnostic X-ray is Compton scatter. This is the one that happens most of the time. So what it is we have an atom here, and you have all the electron shells in the valence band all the way around, and it's got an outer shell electron that's kicked out, boom, is being emitted out of there, and that creates a photon. And whenever that photon happens, that is where we get diagnostic X-rays from. And however, sometimes when they scatter, you don't know which direction it's going to be going in. It's, it's kind of hard to tell. It's like a bowling ball hitting a bowling pin, just knocking everything out of there, I guess is kind of the way that I look at it. But anyways, make sure you shield and protect, because, and stand 90 degrees, of course, whenever you're using the mobile, just to protect yourself from all that X-ray radiation. Okay. And another kind of tissue interaction is the pair production. Pair production happens when your incident beam goes right on in and it collides with the nucleus of an atom. And when that happens and it's got enough energy, usually 1.02 mega electron volts, which is a little too high for diagnostic X-rays, so we don't see a lot of pair production, thank goodness. But if we did, and this was at least 1.02, it would kick those out, and it'd cause two free electrons. One being a regular electron, and the other one is a positively charged electron. And because it's positively charged, it's going to create a little bit of a ripple effect, the annihilation reaction. And of course, these two transmitted to have the energy of 0.51 mega electron volts, which is half of 1.02, which is what was going in there. And it emits another negatron, and that negatron is basically another photon. The energy of an X-ray photon is converted to matter as well. It's not used a lot because of all the energy that's needed. It's used a lot in PET scans and nuke med, and it's out of the target range of diagnostic X-ray. But if we had 10 mega electron volts and we were infiltrating in an atom, we create a tissue problem with called photodisintegration. And this, it's a fun word, I know. Photodisintegration will not occur until it's at least 10 mega electron volts. And what it is you got your incident beam going in and colliding with the nucleus of an atom. And then it responds by going boop. A nuclear fragment is what it does. But it's not very useful in diagnostic X-ray. If it was, well, then, yeah, that'd be not much safe. But anyways, yep, that's my video. Thank you.